Hi, welcome back to the next video on metric space and topology. So in this lecture we will define something called product topology. That's a very interesting and also very helpful uh, topic to start with. But before that, let me just give you a motivation of why we need to do product topology. So just recall that we have in group theory we have seen that product of two groups, right? So what is the product of two groups? This basically means that suppose we have two groups G1 and G2. So let us consider G1 is associated with a binary operation star and G2 is associated with binary operation hash. So then we can define another binary operation, let's say dot on G1 cross G2, such that G1 comma G2 dot with G1 prime comma G2 prime equal to G1 star G2 G1 star G1 hash prime comma G2 hash G2 prime. Sorry. So that means you see that G1 and G1 prime both are coming from G1. So you can apply the binary operation star between G1 and G1 prime. Similarly, G2 and G2 prime both are from G2. So you can apply the binary operation hash on G2 and G2 prime. So that means we are getting two elements in G1 and G1 cross. So it is belongs to G1, this belongs to G2. So of course this dot is closed in this binary operation and satisfy all the group properties. So that means this basically gives that from two different groups we have constructed another group. So there is also the same notion of this product in case of topological spaces. So what is our target? Suppose we are given that two topological space x1 comma tau 1 and x2 comma tau 2. Okay, these two are topological spaces. So our target is to define a topology on x1 cross x2 such that the first property to be satisfied is the first one is the projection, that is x1 cross x2 to x1 is a projection map, that is p1 of x1 comma x2, it is x1, and p2 is mapping from x1 cross x2 to x2, that is p2 of x1 comma x3 is x2. These two maps are continuous, and this is first property, that these two maps should be continuous. And second one is tau is the weakest topology on x1 cross x2 such that condition 1 is satisfied. That means if we can define another topology, let's say tau prime, this is on x1 cross x2 such that this p1 and p2 are continuous with respect to this topology tau, then of course I have tau is inside tau prime, means tau prime is large, it is finer topology than tau. Okay, so in fact it is the weakest one. All right, now to go ahead on construction of this product topology. So this topology tau is said to be, rather let's say will, because we haven't constructed this topology yet, said to be product topology. All right, so to construct with this topology, let us start with a very basic prototype. So in order to give a prototype, let us consider very easiest case that we have. Let us consider x1 to be as x2, both are same as r, and tau1 same as tau2 is same as normal equilibrium topology. All right, so we have r comma tau ed and r comma tau ed. So I will try to construct a topology on r1, r cross r itself, means it is basically r2 with respect to tau ed, such that this can, another topology tau, such that this can be considered to be a product topology. In fact, I will show that the product topology tau that we will construct, in fact the topology that we will construct is basically same as tau ed on r2. Okay, so that means the product topology on on r2 is nothing but the normal equilibrium topology on r2. Okay, so for that case, so remember that to construct a topology, what the things that we can get this, first of all, it is fine if we get a basis, from there we can construct topology, right? Rather, if we don't have any basis, if we get a sub basis, then from there, by taking all kind of finite intersection, you can construct a basis. From there you can construct a topology. Okay, so as this is my primary target, that it has to be same as normal equilibrium topology, we all must have can guess that the basis for this tau must be same as the open balls, right? In R2. Okay, all right, so let us start. So consider that r comma tau ed. So what are the basic open sets here? The basic open sets of this topology is basically set of all the open intervals a comma b such that a is strictly less than b belongs to real number. Okay, now what can be the sub basis of this topology? So it is basically a basis, right? A called as b. So what can be the sub basis for this topology? So remember that suppose we have a real line like this. Okay, so here is your point 0, this is plus infinity, this is up to minus infinity. So anyway, if it is let's say small a and small b, this particular region, so we are considering this one, basically this particular region we are considering. So how can I get a subbasis for this topology? Means I want to get some two sets, or let's say open sets in R whose intersection is a comma this open interval AB. So of course you must have got this idea that basically if we consider this line and again this line, then the intersection region of these two open intervals minus infinity to this and minus infinity to this and a to infinity. This intersection region is nothing but a comma b. So basically this your a comma b is nothing but minus infinity comma b union with a comma infinity. I'm sorry, intersection with a comma b. Okay, so these are the sub bases for this topology of this basis b. Okay, now if we need to define the topology on R2, so we have to first we need to construct some open base on R2 with the help of this basic open sets for normal equivalent topology on R. So for that purpose there is something called open rectangle. Okay, so let us suppose a comma b and c comma d is b, these two are, I'm sorry, open interval in R. Means basically these are the basic open sets. Okay, now if we consider a comma b cross with c comma d, so what is this basically? So that means we have, this is my y axis, this is my x axis. Okay, at certain point here is my 0, here is my a to b, then c to d. So that means we are basically considering this particular region. Okay, I'm just excluding their respective boundaries. I'm just excluding this one. Okay, so this should look like something like that. So this is said to be an open rectangle. Okay, so first I will check that the set of all open rectangles, that is a comma b cross c comma d, such that a is less than b and c is less than d. This is open base for R2 comma tau d. So let us consider U is subset of X. I'm sorry, not X, it R2 is open. Okay, so that means the, now let small x belongs to U be an element. So there exists epsilon belongs to real number larger than 0, such that b of x over epsilon is strictly b of is strictly inside U. Okay, now let us consider an open rectangle like this. Okay, so if it is an open rectangle, let us consider this in center is my small x. So what will be this point? So if I consider this particular line passing through x, So this is nothing but x minus epsilon, this coordinate x plus epsilon. And again, if I consider this particular line passing through this, so this is, let's say it is x comma y, of course. Sorry, there is a small, my bad. So it is x comma y, let's say x comma y, yeah. So this particular point is, this recent distance is y plus epsilon, and this is y minus epsilon. Now how can I get open rectangle around this? So you see that if we make this distance half, if we make this distance half, again if we make this distance half, this distance half. Now if I consider this open rectangle, that means basically I am considering this particular rectangle, this open rectangle, okay, this one. So that means basically I am considering the open rectangle x minus epsilon by 2 comma x plus epsilon by 2 cross with y minus epsilon by 2 comma y plus epsilon by 2. Alright, so you can easily check that suppose x1 comma y1, this belongs to here, so mod of x minus x1 epsilon by 2 and mod of y minus y1 epsilon by 2. Okay, now what about the square root of x minus x1 square plus y minus y1 square is less than square root of epsilon squared by 4, means basically epsilon is epsilon square by 2, right? So this is less than epsilon basically. So that means x1 comma y1, this is inside b x comma y epsilon, so it is the inside is open ball. So that means I can easily say that for if any particular element of this open rectangle is inside this open ball, so basically this, let us consider this open rectangle as rx comma y. So rx comma y, this is inside b epsilon of x comma y. So if I take this in and this is inside u, and if I take the entire union of x comma y of this cells of such u and rxy, then of course it will be same as y. So that means every open set of R2 in normal rectangular topology can be written as any union of certain maybe countable, uncountable, or whatever, any arbitrary union of certain open rectangles. All right. So that means this collection this works as a basic open set or open base for this normal rectangular topology over R2. Okay, so first, so we have seen that normal rectangular topology, there are two kind of open bases. One are the collection of all the open balls, that is of this kind of form, and as well there are open rectangles of this kind of form. In fact, you can easily say that with respect, now I mean from here it is very clear, right, that if we consider all such xy's, okay, in fact for any two particular xy, if I take any other element here, I can again take certain neighbor around this and it will be completely inside open ball. That means itself is open ball. In fact this but condition is true for any open set, so I can itself consider this open ball as an open set. That means each open ball are nothing but the union of certain open rectangles. Okay, similarly we can again show that suppose it's a very small exercise. show that open rectangles also contain open balls. So that means, let me give you a brief idea. That means suppose you consider an open rectangle like this. This is my A comma B. This is my C comma D. Okay. So let us take any particular point here. Alright. So let us take this X comma Y. So take these two distances from A to B. Okay. Take the minimum one, make it half, and prescribe a circle. This circle will be completely prescribed in this open rectangle. Okay, because you are not choosing this point from the corner one. All right, that's why if you take like this here, so this one, whatever point you will choose, it will complete in prescribed circle will be completely inside this open rectangle. All right, so that means this is how one can define them. In fact, you can easily check that these open rectangles are open sets. All right, there is also another way. Like if you know already that these open rectangles are open sets in normal Euclidean topology. That is very easy for you to check. So as these are open sets in our normal Euclidean topology, that means in fact this is a way to construct the open balls around this. So then of course this will be contain this contains certain open ball, right? So this is the main basic formula to check it, that suppose take any particular point, take the minimum of them. Like what is this? So this distance is basically y and this is basically x. So take the minimum of them, make this distance half, and take the and consider prescribed circle around x comma y, and that particular circle will be completed inside this open rectangle. Okay, so this is how one can do this. Is a very good exercise and of course a very fantastic mindstorm game. That means in case of normal Euclidean topology, the collection of all open rectangles and collection of all open balls are basically equivalent to each other. Okay. All right. Now, so what we had in normal Euclidean topology, we had in case of normal Euclidean topology, we had certain basic open sets, and now what we will try to construct some sub-basic open set for this topology. So what is sub-basic open set for this basis basically? So for now on, I will consider the basis. In case of product topology, I now consider the basis, which are basically open rectangles. Okay. So to construct the sub-basis for this topology, sub-basis for the basic basis which is consisted of all the open rectangles. So you see that sub-basis for the basis consisted of base open rectangles. So there is something called open stripes. So what are the open stripes? The open stripes are the form A comma B cross R such that A is less than B belongs to real number, and R cross C comma D such that C less than D. So the open stripes are basically of this form, that suppose it is my R2, okay. So open stripes are basically, for example, suppose this is my AB, this open rectangle, open interval on R. Then A comma B cross with R means basically I'm considering this entire line like this. This is basically you can consider this to be a railway track, right? And is spread up to plus infinity. Let's say, yeah, I mean plus infinity is improper minus infinity. All right. So this is this entire region. This is a tune open stripe. And how does this kind of stripes look like? So suppose we have certain C comma D here. So R cross C comma D means is basically like this. So these are the open stripes. Okay. So this is how one can define. Now you see that is up to minus infinity, this is up to plus infinity. Now you see that what about this intersection point? So this is basically rectangle. Alright. So that means now from this pictorial representation you might have got some idea that it may be the subbasis for this topology, for this basis. So that need a very small check, that let us call this name as S. So S is subbasis for the open base constructed before. Okay. So suppose we consider, let's say, A comma B cross with C comma D is nothing. In fact, it is easy to check that it is A comma B cross with R intersection with R cross C comma D. So let us take any element Z1 comma Z2 belongs to this. So Z1 belongs to A comma B and Z2 belongs to C comma D. Z1 is in here, Z2 is here. So this particular one considered contains Z1 comma Z2 and this one as well contains Z1 comma Z2 because it's Z1 are itself real numbers. So there is nothing more to check. Okay, it's very trivial. Okay, so now you can easily check that if we have certain open stripes, first of all, now let us go back in the ulta direction. First of all, if we had all these open stripes, we can define the open stripe. First of all, if we define the open stripes, from this open stripe we can construct the open rectangles of this form, and once we construct the open rectangle we could define the normal equivalent topology on R2. Okay, we have basically gone from just predicted the topology tau non-equivalent topology. From there we have tried to get some open basis for that, and from there we try to get some basis for that. But now the basic fund is basically in the ulta direction. That means first we have some open stripes. That should be the thing. That first we have some open stripes, because you see that open stripes can be defined in this way as well. Okay, in fact you can check that this is a sub basis for a topology. You know how to check a sub basis for a topology, right? Because you can show that the entire of this open set is basically the entire set x1, x2. Okay, so this is how one can define the sub basis for the sub basis like this. And from this sub basis with all kind of possible intersection, you can construct this open rectangles like this. Okay, and then from this open rectangle you can construct the normal equivalent topology tau ed, and that particular normal equivalent topology on tau ed can be considered as a product topology in R2. Okay, which is generated by equivalent topology on each R components. So now this is a prototype that you have seen. That let me just write it here for your understanding. That so far forward we done. Actually you had to do, we need to go in opposite. reaction. Okay, so this first of all, that is, one is open stripes. From there we have to construct open rectangles. From there we have to construct normal Euclidean topology, and that can be regarded as product topology on R2. Okay, so this is basically a route map for me. Okay, so that means now general case. So consider in general case, suppose x1 comma tau 1 and x2 comma tau 2, these two topological spaces. Okay, so first we have to define, so basically open stripes are basically prototype of subbasis. Open rectangles are prototype of basis, and this prototype of product topology. So first we need to construct the subbasis. So we consider that S to be as set of all x1 cross g2 such that g2 belongs to tau 2 union with g1 cross x2 such that g1 belongs to tau 1. You see that the construction of stripes, we considered this basically at x2 and these basically as x1, and rest of all are same. Okay, because in case of general topology, why we were able to consider this a comma b, because as we are blessed with the topology tau et, where we can visualize the basis for the topology, then it was fine. But for in general topology, we may not be able to construct visualize of course there are some basic open sets, but there we cannot visualize properly. So that's why it is enough to construct, or of course it might much more than, but it is enough to construct consider these entire open sets, all the open sets, okay, instead of the basic open sets. So you're not trying to restrict ourselves instead of basic open set, because that's why because in that case some kind of open sets may be get disregarded. Okay, so my first claim is that S is subbasis for x1 cross x2, whatever topology we already construct. So of course if we consider that to construct show that it is a subbasis for this topology, we just need to show that union of all S, let's say, belongs, we are considering all this as S itself is basically all this S is x1 cross x2. This is how we want to check the each of the open sets. Okay, so there is nothing difficulty to check it. So let us consider any element z1 comma z2 belongs to this. So of course z1 comma z2, this belongs to sum of s, and each x either should look like x1 cross g2, where g2 belongs to tau 2, or should look like g1 cross x2, where g1 belongs to tau 1. Now here g2 belongs subset of x2, so x1 cross g2 is subset of x1 cross x2. Similarly, g1 cross x2 is subset of as well x1 cross x2, because g1 is subset of x1. Okay, so that means for any of the cases g1 comma g2 must belongs to x1 cross x2. So that means union of all s belongs to s is subset of x1 cross x2. So again, now you see that we have considered this open subbasis at set of all x1 cross g2, where g2 is a subset of tau, g2 is inside tau, that means g2 is open in x2. So now you know that x1, this is open in x1 comma tau 1, and x2 is open in x2 comma tau 2. So that means we can consider that, we can consider that, let's say x1 cross x2, this belongs to S itself. That means this is itself an element of this set S. That means it is a subset, it is of course subset of this entire union. Okay. So that means x1 cross x2 is subset of entire union. So means it is basically enough to write it as same. So that means this is subbasis for x1 cross x2. Okay. Now from this subbasis we can construct a basis. So construct a basis. Okay. So how to construct a basis? So I will construct basis B to be as set of all such that Si belongs to S, set of all kind of possible finite intersections, and also I can take their union as well. Let's see. First I will take all kind of possible finite intersections, and then I can take an arbitrary union of them. Okay, means basically arbitrary union of all, let's say Bi, where each Bi is it is enough to write in this way. So Bi such that each Bi is finite intersection of k equals 1 to ni sk. Okay, where sk belongs to the subset topology S. Alright, so now it is just a definition, so let us get some more clear overview of that. So I claim, first of all, let me clear my motive, my claim that B is nothing but G1 cross G2 such that G1 belongs to tau 1 and G2 belongs to tau 2. You see, this one is same as this kind of construction, right? Where it is opening time, yeah, this kind of construction. Here we have just considered the basic open set, but there I am considering the entire all kind of open sets. Okay. So let us prove it. Suppose we have G1 belongs to tau 1 and G2 belongs to tau 2. Okay. Suppose G1 cross G2, this is subset of G1 cross X2, because G2 is subset of X2, as well as subset of X1 cross G2, because G1 is subset of X1. That means G1 cross G2, this is subset of G1 cross X2 intersection with X1 cross G2. Okay. Now so that means G1 cross G2, in fact, it is finite intersection of some members in X, right? In fact, we can write it as. Now, what about the converse one? If I consider any an element, let's say A comma B, from this intersection, so of course A is in G1 and B is in G2, so it is basically same. So G1 cross G2 can be written as finite intersection of these properties. Okay. Now let us consider another kind of finite intersection of this form. So I equals 1 to, let's say, n, which is of the form Gi cross X2 intersection with J equals 1 to m X1 cross H. Okay. Be any kind of finite intersection of intersection from this set. Okay, I just consider any finite intersection where these are basically of this from BI. So these are BIs. These are BIs. These are BJs. Okay. So now let x comma y, these belong intersection of y equals 1 to n. Let us take any arbitrary element from this intersection. Okay. So that means what? X belongs to Gi for all I equals 1 to n. Okay. So that means we have y belongs to Hj for all j equals 1 to m. Okay. So that means what? This will imply that x belongs to intersection of all I equals 1 to m is in Gi, and this is in y belongs to j equals 1 to m Hj. Okay. So that means x comma y, this belongs to intersection I equals 1 to n Gi cross intersection of j equals 1 to m Hj. Okay. Now this is an open set, so it is of the form, let's say, u1 cross u2, because find intersection of open set is of course open set. Okay. So that means this entire union, this intersection basically that we have considered here, this intersection is subset of this intersection. So basically we have got that intersection of I equals 1 to n Gi cross x2 intersection of j equals 1 to m x1 cross Hj is subset of intersection of I equals 1 to n Gi cross intersection of j equals 1 to m Hj. Okay, this is how one can construct the map. So one side is clear, that this intersection one side is clear. Now we have to another side, that this particular one is inside this one. Let us see. So again, let us consider another element. Let's say x prime comma y prime. This is inside. Intersection of I equals 1 to n gi plus intersection of j equals 1 to m h. So of course then x prime belongs to intersection of I equals 1 to n gi, means this belongs to x prime belongs to intersection of all I equals 1 to n x prime comma y prime. This belongs, because y prime is itself in y in x2, so this belongs to gi cross with x2. And similarly y prime belongs in intersection of all j equals 1 to m h. So that means x prime comma y prime belongs to intersection of all j equals 1 to m x1 cross h. Okay, so that means x prime comma y prime, this belongs to intersection of all I equals 1 to n gi cross x2 intersection with j equals 1 to m x1 cross h. So both, now that means this one is basically a subset of this one. So that means we have already, that means final story is that intersection of I equals 1 to n gi cross intersection of j equals 1 to m h, this is same as all kind of g1 n gi cross x2 intersection with j equals 1 to n x1 cross h. So that means now if I take the all kind of now if we take arbitrary union of this form, is that means basically taking arbitrary union of this form. Okay, that means each open set basically of this these are basically basic open set which is generated by the sub basis we have defined here, like this particular sub basis. That is by this particular sub basis. Okay, so this is the basis generated by this particular sub basis. All right. So now from this topology, so we have got the basis for this product topology. I'm sorry. For this product topology is basically is from G1 cross G2. Now from this topology one can construct the product topology. Okay, so the tau, let's say B, is generated by this topology, means it is any arbitrary kind of union, small I belongs to capital I, Bi. This is basically, I mean, this is of the form this topology. I'm sorry, I forgot to mention, I just erased a small mistake. This is a basically topology. I mean, from the topology subbasis to the construct topology, we used to give the union, but for now we don't need the union. We just consider it is enough to consider the any kind of normal intersection. Okay, or finding class of all intersection, class of all find intersection. That is enough to consider the basis. So this is the topology. Okay, so what is said to be the product topology. I request you to rectify your, I mean, I'm sorry, my fault basically, where consider topology. I mean, this basis. Okay, the basis which is constructed by the sub basis nothing but all kind of finite intersections. But once you want to construct the entire topology from a sub basis, then you have to take the all arbitrary union of all such finite intersections. Okay, that is basically how we construct the topology from a basis. Okay. So now let us see that whether our target is getting satisfied or not, means the projection maps are continuous or not. So it is enough to consider a projection over any particular site, like, and another side will be similar to the one, like uh, just a mirror image of that on one side. So for our convenience, let us consider P1 is mapping from x1 cross x2 to x1 such that x1 comma x2 is mapping to x1. Okay. So to prove that it's continuous, I have to show that the inverse image of the set is open. Okay. Inverse image of open set is open. That means suppose let us take G1 is open in X. So P1 inverse of G1, this has to be open. Okay. My claim that this is open in x1 cross x2. Okay. So you see that G1 is in open in x1. So of course you can construct a sub-basic open set of this from x2. Okay. Now as it is a sub-basic open set, that means this belongs to S itself. That means G1 cross x2 is must be a basic open set. This must belongs to P. Okay. So that means G1 cross x2, this must be open in x1 cross x2, right? It's very trivial. So I will show that P in P1 inverse of G1 is same as G1 cross x2. So let us consider that G1 comma G2, this belongs to G1 cross x2. Okay. So what about P of G1 comma G2 is nothing but G1, so this belongs to G1. So G1 comma G2, this belongs to P1 inverse of G1. That means G1 cross x2, this is subset of P1 inverse of G1. Okay. Another property, again, suppose we have H1 comma H2, this belongs to P1 inverse of G1. So of course P1 of H1 comma H2 is nothing but H1 belongs to G1. So that means H1 comma H2 is inside G1 cross X2. So that means P1 inverse of G1 is same as G1 cross X2. That means this is opening X1 cross X2. So that means P1 is continuous. Okay. So similarly you can prove that P2 is continuous. In the same proof, that's basically a mirror image of this proof. Okay. So that means the target that we have considered is basically is fulfilled by our case. Okay. Now, and just a small check is there, that is, we have said that the weakest topology that one can think of. So suppose we have tau prime be another topology on x1 cross x2. Okay, so my claim is that tau is inside tau prime minus tau product that you have defined. So what is the basic open sets of this product topology? These are basically of this from G1 cross G2. So if we can show that all the basic open, each basic open set is inside open in tau prime, then we are done, right? So for that purpose, let us consider basic open set in tau product. Okay, tau product means that topology that you have defined, like from here. Okay, there is a tau product. So yeah, let us not tau p. Let us name it as tau product. Okay? Yeah. Now we have already seen that what is P1 inverse of G1. P1 inverse of G1 is G1 cross X2, and P2 inverse of G2, it is X1 cross G2. Now we have assumed that tau prime is another topology on x1 cross x2 such that each p1 and p2 are continuous. So p1 inverse and p2 inverse g1, p1 inverse of g1 and p2 inverse of g2, this has to be open in x1 cross x2 under this topology tau product. That means g1 cross x2, this has to be open in tau product, and x1 cross g2, this has to be open in tau product. Now if I take the intersection of g1 cross x2 and x1 cross g2, then I will just get g1 cross g2. So think about g1 cross x2 intersection with x1 cross g2. Okay, that's what I will get. So that means this has to be open in x1 cross x2 under the topology tau prime that I have assumed. That means tau is product, is subset of tau prime. So it is the weakest topology that one can think of. All right. So this is what we were trying to figure out from the prototype, that how to construct a topology from any two particular topologies. So this can be extended up to any arbitrary any finite number of open topologies, or in fact arbitrary number of topologies itself. There is no other issues. Okay, so this is a product topology. So in the next class onwards, we'll see something called compactness and connectedness, and after completing all those cases, we'll again move back to product topology to see that how the connectedness, compactness are getting preserved or not getting preserved under the product topologies or not. Okay, so you just revisit all these things that we have discussed today, and also of course the previous things, because I don't want you to lose the previous concepts. And hopefully from next class onwards we will be able to start with the connectedness and complex properties. Okay, thank you very much for your patience. Bye.